Hi, I'm Alia Yan, an application engineer from BetterSize. This presentation is about dynamic light scattering microrheology, one of the latest updated features of the BeNano series. This presentation is divided into 4 sections: fundamental concepts, principles, features and benefits, and key applications. The first part of this presentation is fundamental concepts of rheology. At the beginning of this part of the presentation, we might have some questions like, why is rheology important? Rheology is the study of how materials deform and flow, or more generally, how viscous they are when subjected to a constraining force. And because rheological information provides insight into formulation development and product processing, rheology has been the key to our understanding and appreciation of the properties and behavior of viscoelastic materials. Rheology also affects product performance in terms of taste, hardness, shape, and usage. In addition to these applications, phase behavior and rheological properties can be obtained for stability studies. So, how do we come to understand rheology? Let's start with some fundamental rheological concepts. We need to discuss 2 different properties of materials in order to understand the rheology of materials. The first is viscosity, which is defined as the ability of a fluid to resist flow and is described by Newton's law of viscosity, which calculates viscosity as the ratio of shear stress to shear strain rate. And the second is elasticity, which can be defined as the intrinsic ability of a solid to resist deformation. The degree to which a material can resist deformation is defined by Hooke's law, which states that the elastic strength of a material is the elastic modulus. The elastic modulus of shear is equal to the ratio of shear stress to shear strain. The behavior of solids and liquids is quite different from a rheological standpoint. However, some materials, such as gels, exist as a mixture of a liquid phase within a solid phase, so they exhibit both viscous and elastic properties, and they are known as viscoelastic materials. So how do we describe the rheological behavior of a viscoelastic material? This is done by calculating what is known as the complex modulus, represented by the G star for shear stress. The relation between the complex modulus and the storage and loss moduli is that of the relationship between the 3 sides of a right triangle, where the complex modulus is the hypotenuse. It is therefore natural to formulate the theorem that the tangent of the angle delta is equal to the opposite side over the adjacent side, or G double prime over G prime. For a viscoelastic material, the complex viscosity eta star is the complex modulus of the system over the angular frequencies, and the creep compliance, which we have defined as J, is the shear strain divided by the shear stress loading over time. As we all know, viscoelasticity is the property of materials that have both viscous and elastic properties when they are deformed. In a static state, which means the frequency is 0 Hz, we can classify viscoelastic materials into 3 typical types: viscoelastic solid, viscoelastic liquid, and gel. For a viscoelastic solid, G' is constant and dominates at low frequencies, while G double prime increases with increasing frequency and dominates at high frequencies. It has a stiff consistency when resting but deforms readily when subjected to a sufficiently large force. For a viscoelastic fluid, G double prime is more than G' at low frequencies and G' is more than G double prime at high frequencies. That's why a viscoelastic fluid behaves like a liquid at a low angular frequency. For a gel-like material, G' and G double prime are parallel over the entire frequency range. So, what kind of instruments should we use to measure the rheological properties of a material? We have different technologies for rheological characterization. In general, we can divide these technologies into 2 types. The first type is conventional mechanical rheology, which is still widely used. For example, a rotational rheometer simply compresses the sample and applies rotational shear to deform the sample. However, the microrheology technique has recently been developing more rapidly. There are 3 types of microrheology research methods in the field of modern microrheology technologies: particle tracking analysis, dynamic light scattering, and diffuse wave spectroscopy. So, what are the differences between mechanical rheology and microrheology? In fact, mechanical rheology involves applying a small amplitude oscillatory shear strain and then measuring the resulting shear stress. And it provides an average measurement of the bulk response. But its limitation is that it can only be used to probe frequencies of up to a few tens of hertz. In contrast, microrheology is a technique used to measure the rheological properties of a material by measuring the motion of tracer particles. Microrheology allows elastic and viscous properties to be measured quickly and without contact. Depending on the force applied to the tracer particle, there are two types of microrheology: passive microrheology and active microrheology. Passive microrheology uses inherent thermal energy as applied force to move the tracers, while active microrheology uses externally applied forces to move the tracers. As a result, microrheology has several benefits, including the ability to measure samples with very low viscosity and elasticity and to measure over a wide frequency range. Compared to mechanical rheology, the sample volume is very small, only a few microliters are required. It can also provide local viscoelastic information such as G', G', J and eta star. In addition, microrheology can show good agreement with mechanical rheometers. It can be used as a complement to mechanical rheology. Let's move on to the next part: the principles of DLS microrheology. When talking about DLS microrheology, it is important to note that it is a passive microrheology that applies no external forces to the tracer particles. And it can extract linear rheological properties from the motion of tracer particles undergoing thermal fluctuations in a system. In a DLS microrheology experiment, tracer particles undergo Brownian motion in a system at thermodynamic equilibrium. The motion of the tracers then causes random scattering fluctuations, and DLS microrheology measures the autocorrelation function of the light scattered by the particles. The relation between the MSD of the tracer particles and the autocorrelation function of the scattered light is then obtained from the correlation function. When performing DLS microrheology measurements, the choice of tracer particles is very important. A key requirement is to minimize particle matrix interactions. If there is any significant physical or chemical interaction between an embedded tracer particles and its surroundings, this may alter its local environment and affect its diffusivity. Second, the tracer size used in DLS microrheology measurements can have a significant effect on the extraction of rheological parameters. In addition, the appropriate tracer concentration must be considered for good dispersion, and the scattered signal should be dominated by the tracer particles. After that, I would like to introduce you to the measuring process of the BeNano series. The first thing to do is input the particle size of the tracer particle. Then the instrument measures the intensity of the scattered light to obtain the correlation function, and from that we can obtain the MSD curve. Finally, the rheological information such as G', 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 and E* can be extracted from the MSD curve. Let's look at the data processing of the BeNano series. The DLS microrheology measures the scattering fluctuations. Then the correlation function and the MSD curve are derived from the scattering fluctuations. And from the MSD curve, we can obtain the rheological information such as elastic modulus G' and viscous modulus G', complex viscosity eta*, and creep compliance J. Then I would like to talk about the features and benefits of the BeNano series DLS microrheology. Compared to the mechanical rheometer, DLS microrheology can access the very high frequencies needed to measure the short timescale dynamics of low viscosity materials. And it can cover much wider and higher frequencies than conventional mechanical rheometers in a single test. Therefore, DLS microrheology is well suited to the rheological study of dilute, weakly structured macromolecular solutions. DLS microrheology requires very small sample volumes, which can be reduced to microliter volumes. As for the BeNano series, the sample cells are shown as the image, and the minimum volume can be less than 50 microliters. DLS microrheology can characterize materials that are not available in large quantities, such as protein formulations or those in early development. It can also characterize expensive, rare, or fragile samples. Because DLS microrheology is a passive microrheology, no external forces are applied to the tracer particles. This makes DLS microrheology well suited for highly strain-sensitive systems, as it can probe the linear dynamics of materials under conditions of very low applied strain. DLS microrheology measurement can effectively detect a full range of measurement frequencies simultaneously using aggregation statistics derived from the Brownian motion of tracer particles. And BeNano series microrheology measurements are performed in 1 to 2 minutes. As a result, both the measurement and the data processing are simple and fast. In summary, there are many features and benefits of DLS microrheology, such as wide frequency range, extended to high frequency up to MHz, small sample volume requirement, which is less than 50 microliters, non-destructive measurement, and simple and rapid rheology measurement. DLS Microrheology is available in our BeNano series instruments except BeNano Zeta, and some specifications of BeNano series microrheology include frequency range from 0.2 to 13 billion radian per second. The detection angle is 90 degrees or 173 degrees. The tracer particle size from 0.3 to 1 micrometer. The sample volume from 45 microliters to 1.5 milliliters. The temperature range from -15 degrees Celsius to 110 degrees Celsius. I will then go on to introduce you to the key applications of DLS microrheology. We want to focus on the applications where microrheology can make the biggest difference. When it comes to small sample volumes, non-contact measurements, high frequencies or sensitivity, the benefits of microrheology can be significant. Examples include weakly structured solutions, dilute solutions, low viscosity materials, and strain-sensitive materials. As a complementary technique to classical mechanical rheology, most industries requiring rheological measurements can benefit from microrheology. DLS microrheology is well suited for polymers, proteins, gels, and biopolymers, and the industries most interested in this technology are biotechnology, pharmaceuticals or life science, food, cosmetics, but also academic research. I will now give some examples of how BeNano DLS microrheology is used to obtain rheological information. The first one is sucrose solutions. They were prepared at concentrations of 25%, 40%, and 50%, and 10 microliters of 400 nanometers. Negatively charged polystyrene spheres were added to the samples as tracer particles, and the viscoelastic information of the solutions was obtained by microrheology. The MSD curves show that higher sucrose concentrations result in lower MSD values and lower tracer particle velocities. From the viscoelastic modulus curves, the solutions showed a strong viscosity and the concentration range from 25% to 50%, and the viscoelastic moduli increased with increasing concentration. From the complex viscosity versus frequency curves, in the relatively low frequency range, the complex viscosity basically did not change with frequency variation, while in the relatively high frequency range, the complex viscosity showed a certain downward trend, indicating a weak shear thinning property. Another sample is BSA solution. BSA solution disperses well at low temperatures. However, it is thermally denatured and forms protein agglomerates when heated. This is because the molecular structure of BSA changes from linear to branched from 25 degrees Celsius to 70 degrees Celsius. Therefore, the solution properties change significantly. Using BeNano's microrheology, we determine the viscoelastic information of BSA solutions at different temperatures. For tracer particles, 10 microliters of negatively charged 400 nanometers polystyrene spheres were added to each sample. The results showed that the viscoelastic modulus of the solutions increased at 70 degrees Celsius compared to 25 degrees Celsius. This is due to the formation of macromolecular aggregates by thermal denaturation of BSA, and the formation of aggregates dramatically increases the viscosity and elasticity of the sample. Comparing the temperature dependence of BSA particle size and the temperature dependence of light intensity, the complex viscosity also showed a rapid increase at about 70 degrees Celsius. Now, I have made a summary of the DLS microrheology of the BeNano series. In this talk, I cover the fundamental concepts of rheology, the principles of BeNano series DLS microrheology, its features and benefits, and the key applications. But there is much more to BeNano than that. More technical and application notes will be published on our website and await your exploration. This is the end of the presentation. Thank you for watching, and I hope you found this video helpful. Please feel free to leave any comments or questions below and check out the BetterSize website for more detailed information on each instrument.